Now let's take a look at Appendix B of Chapter 1, where we evaluate the overall fit of the regression line. Okay, previously we looked at the overall fit or statistical significance of the individual coefficients. Okay, but it's also useful to see how the overall model, the entire model, is performing statistically. Okay, so the first statistic we want to think about, and the one that we'll make most use of, is the R-squared value. Okay, the book calls it R squared, and then mathematically it's R raised to the power of 2. Okay, another term for it is the coefficient of determination. Okay, and what it measures is the amount of the variation in the dependent variable that is explained by the regression or the independent variable in a simple regression, or all of the independent variables in a multiple regression. Okay, so its range is 0 to 1. You can see that it won't be greater than 1 because this is a fraction, and it's equal to the explained variation divided by the total variation. Okay, and as the value of the R-squared statistic moves closer to 1, that indicates that you have a better model or a better fit. The straight line, the linear regression line, fits the data, the scatter plot, better. Okay, now one word of caution, an R-squared that's not close to 1 is not necessarily a bad model. There's lots of cross-sectional data that doesn't have a high R-squared. Okay, R-squared can be useful for comparing different models. Okay, so let's not get hung up on data sets that have low R-squareds this semester. Okay, when we move to Excel, you'll see that the explained variation is called the SS regression in our analysis of variance table, and the total variation is the SS total. Okay, SS stands for sum of squares. And I'll let you go back to your statistics course and review where the sum of squares comes from. Okay, so in Excel, we've got this analysis of variance table, and the sum of squares for the regression. So this is the explained sum of squares regression. With these data, it's over 301,000, and then the total sum of squares is 402,000. So 3 divided by 4 is about 75. So we would say that the price variable explains about 75% of the variation in the quantity of sales. You know, once we start thinking about multiple regression, when we add more independent variables to the regression model, the R-squared statistic will always rise. So one way of penalizing a regression model for throwing the kitchen sink in, okay, is to use the adjusted R-squared. Okay, the adjusted R-squared is going to be a statistic that's lower than the R-squared because there's a penalty for the number of independent variables that you use, which is the symbol that we'll be using is K. So K is the number of estimated coefficients. So the adjusted R-squared, or sometimes called the R-bar squared because it has this notation, R with a line across it squared. Okay, so that's equal to 1 minus the R-squared multiplied by this ratio. The sample size minus 1, and then the sample size minus the number of regressors or independent variables. And note that as the number of regressors increases, this ratio will be greater than 1. And 1 minus R-squared multiplied by the fraction on the right will rise above 1 minus R-squared. And so 1 minus the expression in the brackets will reduce r bar squared below the r squared statistic. Okay, in Excel, we're looking for SS residual divided by the residual degrees of freedom. And that formula is not quite correct, so let me type in 1 minus. Okay, and so let's go to the Excel output, and here's MS is the notation for the sum of squares divided by the degrees of freedom. And to calculate the MS for the total sum of squares, you would divide 402,000 by 9 to calculate the adjusted R squared using the formula, the first formula. And in this example, I've calculated 0.72, which is the adjusted R squared, which you'll find in the regression statistics table. Okay, so if you multiply 0.275 by 9 and then divide by 8, and then subtract that from 1, you get 0.72. Okay, another statistic that you see in Excel output is the F statistic. And that is a ratio of the total variation that's explained, which is the regression sum of squares, divided by the degrees of freedom. So it's the total variation explained divided by the total unexplained variation. So if you explain, then the unexplained variation is the sum of squares, the residual sum of squares, but divided by its degrees of freedom. So the larger the F statistic relative to its critical value, the better your regression is doing. And along with the F statistic, you'll get a p-value to tell you the chance that your regression model is basically a null model that explains nothing. Okay, and there are F critical value tables that you'll find in a statistics book, and you can look up the statistic based on a numerator degrees of freedom and denominator degrees of freedom, and that'll give you a critical value. And if your F statistic is above that, then your model is statistically significant. But we can just use the Excel output, and our F statistic of 23.94 is significant at least the 95% confidence level, because our p-value, the significance F, is lower than 0.05. Then our F value is equal to the MS for the regression divided by the MS for the residual. Okay, those two numbers are here, and in the first entry, I've shown how that's calculated, and that's equal to 24. So we've got a good model. Okay, and then a final thing is to understand what the standard error of the regression is. Okay, the standard error of the regression, we'll call it S sub E, is equal to the square root of the residual sum of squares, basically the error terms, that's calculated from the error terms, divided by the sample size minus the number of regressors minus 1. If you take the square root of that, that's the standard error of the regression. And that's useful for constructing confidence intervals for the dependent variable. So here, using the rule of thumb number, the 2, which is the rounded up 1.96, the critical value for the t statistic at the 95% confidence level. If you add and subtract 2 times the standard error of the regression divided by the square root of n, the sample size, and you get a 95% confidence interval around a predicted value for y. And then looking in Excel, you can see how that's calculated. 112.22 is equal to the square root of the MS for the residual sum of squares.